you everyone for attending this webinar series. As Dominic said, I'm going to pick up where he kind of left off. I'm going to kind of explain how, as a designer, I would use this new guide to streamline my design. So first and foremost, as Dominic said, let's remember the guide is not meant to be read cover to cover. You may have seen it was 400 some pages. And as Dominic showed, the idea is not to sit down and read it at night and understand how to do steel bridges. The intent is to use the design guide as you're doing your design and walk through the quick links and help you understand more about the design you're accomplishing. So as I walk through the presentation here, let's keep this example in mind. I'm going to refer to it a little bit. This is actually example 1 from the Steel Bridge Design Handbook. It's a simple bridge. It's a routine bridge. It spans at 140, 175. You can see the cross frame spacing, the section lengths, very routine, straight I-girder bridge that we would normally see. Nothing crazy about the girder spacing or anything like that. 3 spaces at 12 foot, a 9.5 inch deck thickness. The haunch is there. Yeah, this is all just information. But keep this kind of bridge in mind as we walk through this guide as what the routine type of bridge is that we're looking to design today. And using this guide to help us walk through a couple of the design scenarios that we want to discuss here. So what I want to take you through today is how to look at the live load force effects, otherwise known as the live load distribution factors. Girder Flexure design, we'll touch on the general and the constructability checks. We'll talk about splice design, and then we'll kind of wrap things up. So these 4 topics above the summary are really what we're going to focus on here today, and how I would use the design guide to help me do those particular calculations or understand those particular calculations that are associated with each one of those. So let's talk about live load force effects for Flexure. So our objective here is to come up with the live load distribution factors for Flexure for our example bridge. Okay. I always like to start, you saw Dominic talk about this, I always like to start with the general flow of the design task, page 15 of the PDF. If we go ahead and click on the number 6, live load force effects for Flexure, it'll take me to this page in the guide, the design task links page. And you saw Dominic talk about this in his example. There are several sections here. The green section is the quick links to the applicable AASHTO LRFD bridge design provisions with the discussion. The orange color is the quick links to helpful industry guidance, design guides, references, and possibly some examples that may be out there. And then last but not least is the blue, and those are quick links to useful tools. So I'll say this now and I'll repeat it later. This really gives you the roadmap to all the information that's out there on these particular design tasks, whether it be live load distribution factors, girder flexure design. A lot of times, there's a lot of references out there. This puts it all in one place for you as a designer. So let's take a closer look at the quick links with regard to the AASHTO LRFD bridge design provisions with the discussion. So first and foremost, I'm concerned about the live load distribution factors for the interior beams. So as Dominic showed, I would come here and click on the section, the 4.6.2.2.2b, to find out what the guide has to say, what discussion that it has to give with regard to live load distribution factors for interior girders. And as Dominic had showed, it would bring up the determination and discussion for that particular section. So linking it directly with what's in AASHTO, Article 4.6.2.2.2b, interior beams with concrete decks. Now, this is what's in the guide. This provides background, this provides discussion and whether or not that section is applicable to my particular bridge. Let's take a closer look. You'll see right at the top there, it says partially applicable. What that means is parts of the article are applicable to the design of routine steel I-girder bridges. Other parts are not applicable. If you're familiar with this section, this discusses the live load distribution factors for all types of bridges. Okay, so obviously it's only going to be partially applicable because we're designing a steel girder bridge. Right here in the first paragraph of the discussion, it points me right to where I need to go. So it says the equations in the 3rd row of table 4.6.2.2.2b-1 are the only ones applicable to our example bridge, our routine steel I-girder bridge. So I would have AASHTO open on my other screen, I would take a look. I would go right to that table, the 46222B-1. And lo and behold, right there in the third row of the table is what I really need to know. I don't need to be concerned about anything else in that particular table. This tells me right here, it's for a concrete deck on steel beams, as the guide said. So my distribution factors are calculated for the one design lane loaded, and then 2 or more design lanes loaded right there. And I'm going to fall within the parameters within that range of applicability because that I'm designing a routine steel girder bridge. What else does it say in this discussion part? Well, there's some important information, as Dominic kind of alluded to as well. Important notes: multiple presence factors, MPFs, are already included in the live load distribution factors from that table that I just showed previously in ASPE. So I don't want to be applying additional multiple presence factors to those computations that I come up with from that table. However, it does go on to say for fatigue, the multiple presence factor of 1.20 should be removed from the one lane loaded live load distribution factor. So the live load distribution factors in that table are for strength and service evaluation, but for fatigue, I need to be sure I remove that multiple presence factor of 1.20 on the single lane or the one lane loaded. So it tells you there, very clearly on how I should be applying or not applying the multiple presence factors with those live load distribution factors. What else is in here in the determination and discussion section? Well, it gives you links to really good resources that are available in the industry. Again, as I had said before, this guide really provides the roadmap and provides all the information you need that may be out there to help you with the design. So the first one is the reference manual for the NHI course, Load and Resistance Factor Design for Highway Bridge Superstructures. And this reference obviously provides a lot of good resources with regard to designing a girder bridge and pinpoints some of the calculations needed for live load distribution factor. Then again, down there at the bottom shows the NSBA LRFD assignment program, a line girder analysis software program that actually automatically calculates the live load distribution factors for interior girders. So let's go back to our design task links page. We talked about the green section, which is the quick links to the applicable AASHTO LRFD bridge design provisions with the discussion. But now let's move on to the orangish section of the quick links to helpful industry design guidelines, references, and examples. And let's take a closer look. You can see right there at the top of the screen, again, is that NHI course manual for the load and resistance factor design of highway bridge superstructures. And not only does it provide me a direct link to that available on the internet, but it tells me what sections to go look at. Section 4.4.1, general 4.4.2 for live load distribution factors, and then influence lines in 4.4.3. So I don't have to go open the manual and start searching for live load distribution factors. The guide tells me right where I need to go. Additionally, there's other examples down below, or other information, I should say, down below from the Federal Highway Administration's Steel Bridge Design Handbook. Here, if I go ahead and click on Design Example 1, which is actually the example we're looking at, you'll see it takes me right to that, it would open up in another screen, that design example right there on your screen, so you can reference that as well. And in there are more calculations and more examples on following through the live load distribution factor. So if the NHI course doesn't satisfy your taste, you can obviously go to one of these handbook examples as well to get more information. So back to our design task links page for live load force effects for Flexure, the live load distribution factors. Let's take a look at what's in the blue box. This is the quick links to useful tools. Okay, this is where the guide will provide direct links on the internet to the useful tools that are here. And as you can see, NSBA's LRFD Simon line girder analysis program is linked here. Why is it linked? Well, it can do the calculations for you, and it can do the full girder design for you for a line girder analysis, but it also does the live load distribution factors. Now you can go ahead and calculate those manually if you want and input them, but Simon also allows you to put in some parameters for your particular bridge, and it'll calculate the distribution factors, the live load distribution factors on its own. So going back to our example, now that I've reviewed the discussion section from the guide, I've opened up the LRFD, I found the particular equations. I used the NHI course and the Steel Bridge Design Handbook as some examples to understand how to calculate these live load distribution factors. I feel confident enough that I can actually perform these calculations and understand what all the variables are and how to come up with those live load distribution factors for the interior girders. And I'll go ahead and do that. And following through the example, these are the numbers, these are the calculations. What's important in this discussion here today is how to use the guide and not necessarily the numbers that are coming out from the calculations that I'm showing. So let's move on. Go back to our design task links page. I did interior girders, but now we should probably look at the exterior beams as well, or the exterior girders. So what does the guide have to tell me with regard to that? Let me go ahead and click on exterior beams. And again, that'll take me to the determination and discussion section of the guide for exterior girders. This section's a little longer, but it tells me it links up right again with the AASHTO LFD bridge design specification, article 4.6.2.2. I think I got enough twos in there. But let's take a closer look at what this article has to say. Well, again, it's partially applicable, again, because this section deals with all bridges, not just steel girder bridges. So the whole section, the whole article is not going to be appropriate for my particular discussion, or for my particular bridge, I should say. And this is in the discussion. Now, the equations in the third row, the equations, again, it tells me are in the third row of table 4622D-1, which is the exterior girder or the exterior beams. And only those ones are applicable. So again, I go to this is a different table from the one I showed before. This is the one for exterior longitudinal beams. And lo and behold, again, the guide points me right to where I need to look. I don't need to worry about anything else in that table. I need to worry about this third row in the table. And it tells me what I need to use for one design lane loaded or two or more design lane load, two or more design lanes loaded. And those are the equations there that I would use to calculate my live load distribution factors for an exterior girder. However, if I read some more within that section in the discussion and determination section of the guide, it tells me for exterior girders, it is suggested to consider the special analysis of equation C4.222D-1, which is in the commentary section of that particular article in the AASHTO LFD bridge design spec. So let me go look at that. What it says here, this special analysis assumes the entire cross-section rotates as a rigid body about the longitudinal center line of the bridge. Distribution factors for the exterior girder are also computed for 1, 2, and 3 lanes loaded using the following formula. And it gives me the formula there. And if I read some more within the guide, and I read some more within the AASHTO LFD, this of course applies to exterior girders. And it's kind of like a pile group analysis, if you would. Considering the rigid body rotation of the cross section, and it encourages me to go ahead and use this as one of my live load distribution factors as well, in addition to what's shown in that table. And of course, that again, as I showed before, that was mentioned within the guide, within the determination and discussion section. So now again, similarly as before, that I've gone through all the I've read through what the guide gives me. I've read through the particular AASHTO section, the exact row, and the commentary for that special analysis. I took a look at the NHI course again, the NHI course manual that was referenced, and then also the Steel Bridge Design Handbook, which is also referenced. And I can feel again confident in developing the live load distribution factors for the exterior beams. In this case, for 1 lane loaded using the lever rule, 2 or more lanes loaded. It's just a modification of the the interior girder factor by that E, which was in that table. And then I can go through and do my special analysis as well, that rigid body rotation or kind of pile group action, and compute all of the live load distribution factors and determine which ones are the governing ones. And you can see right there, 2 lanes loaded is the governing live load distribution factor for the exterior girders. Again, using the guide and using the resources provided in the guide to feel confident in making these computations. And again, as you probably noticed in the quick links for applicable tools, the LFD Simon program was shown as well, which could help you develop the live load distribution factors, not including the special analysis. So in some cases, that special analysis needs to be developed outside of the LFD Simon program, and that states that actually within the guide for exterior beams as well. So, of course, there'd be other details and other things to look at, for shear and so on and so forth with regard to live load distribution. But let's go ahead and move on to, if I was doing girder flexure design and how I would go through and do that. So again, it's important to remember for girder flexure design, the AASHTO LRFD limit states that we need to follow through on. Okay, there's constructability, the service limit state, fatigue, the strength limit state, and then the extreme event limit state. Now I do have an asterisk next to constructability. It's not necessarily a defined AASHTO LRFD limit state, but it is often treated as one. But it is invoked under the strength limit state, and that's checking our deck pour sequence on the bare steel and making sure our girders are satisfy the design provisions, kind of in the non-composite state, we'll say, before the deck is hardened. If you have more questions or want more information with regard to the limit states in the AASHTO LRFD, I suggest the Steel Bridge Design Handbook chapter, volume 10, I should say, limit states design or limit states, and that gives you more discussion with regard to the limit states. And again, I didn't go through it here, but this is also included within the routine design guide as well. But it's important to recognize these limit states. Why? Well, these limit states are also shown in the general flow of design tasks. You have constructability, service limit state, the fatigue and fracture limit state, and then the strength limit state. So all those are right there. But you may be asking yourself, well, where is the extreme event limit state? Why is that not shown? Well, if I read under the general considerations, it's going to note, the guide tells me that the extreme event limit state is beyond the scope of superstructure design for routine bridges. So, and that is shown there in the design task item, design task item 1, general considerations. So, basically saying, for the bridges that are covered by this guide, the extreme event limit state is not going to be considered. So keep that in mind. That's why it's not shown with this list of limit states here. So my primary objective now is to perform the girder flexure design for constructability. So again, I would start with the general flow of design task on page 15. I'd go ahead and click on general flexure or girder flexure design general, because I think I should start there and see what the guide has to tell me about that. Again, we come to our design task links page, which is shown here. Now let's look at the green section again, the quick links and the applicable, how the AASHTO LRFD bridge design provisions may be applicable to my particular bridge with particular discussion. Now, first and foremost there, it shows the composite section stresses, and it has a lot of articles listed here. And you heard Dominic talk about accessing the bookmarks as well. I always have the bookmarks open on my PDF browser, we'll say. So if I want to know what all those are, your 610, 111, 1A, 1B, 1C, what are all those? I can quickly look over at the bookmarks page, or I'm sorry, look at the bookmarks over on the left of my screen and see, well, yeah, the 1A is a sequence of loading, 1B is stresses for sections and positive flexure, 1C sections and negative flexure, and so on and so forth, to have an understanding of what those are. So you can work the PDF together as one, having the bookmarks open on the left and then being able to click through over on the right. Let's go ahead and see what it has to say about Article 610.111A. Again, this is the sequence of loading. And is this applicable? Yes, it's applicable in its entirety to the design of routine steel I-girder bridges. And right here in the discussion, it tells me which loads are to be applied to which section properties, or which section and what section properties to use. Where DC1, my non-composite dead loads, get applied to the bare steel. My composite dead loads, DC2, are applied to the long-term transformed composite section, the 3N one. My DW, my wearing surface, if I have it or will have it, those are also applied to the 3N section, the long-term transformed composite section. And then my live load plus impact load forces or moments are applied to the short-term transformed composite section, the N section properties. So it's basically telling me what section properties to apply to resist which loadings on my bridge. Do I have a deck on? Do I not have a deck on? Right? And is that can I count on that deck to help resist those forces, DC2, the DW, and the live load plus impact. So what else does this section tell me? Well, it alerts me to the fundamental section properties, which you often see. My yield moment, my plastic moment, and things along those lines. And again, it just lists out the particular code sections or the particular AASHTO LFD sections. But if I want to know a little bit more about what those are, I can go ahead and look at my bookmarks on the left side and see what D6.1 is the plastic moment, D6.2 is the yield moment, and how I can compute those, and D6.3 is the depth of the web and compression. So let's go ahead and click on D6.1. What is that? Well, that is the plastic moment. The D6.1 aligns with Appendix D and the Appendix D of Chapter 6 in the AASHTO LRFD Bridge Design Spec. Right here, it tells me it's conditionally applicable. So some or all of the article may be applicable to the design of routine steel eye-girder bridges, depending on the circumstances you have. So what's given here, it gives you a lot more background discussion on the plastic moment, when it's applicable, how you should apply it, where the calculations are to come up with this, and how to come up with that. And with direct links to AASHTO articles, or giving you the AASHTO article, not a direct link to the LRFD itself. And explains what the plastic neutral axis is, explains what the plastic moment is, and how that's used in your computation. So say I'm a little fuzzy on that. What kind of quick links are available in design guidelines and references? Well, first and foremost is the reference manual for the NHI course. Again, you heard us talk about this a lot, for load and resistance factor design of highway bridge superstructure. And right there, it tells me section 6.4.5.2 discusses the plastic moment, 6.4.5.3 the yield moment, and so on and so forth. So if I go ahead and click on that reference manual, it'll open up on my screen and take me right to it. Now I do have to go find section 6.4.5.2, but you can see it explains in detail and provides a lot of background on the calculations to come up with the plastic neutral, where the plastic neutral axis is located, and how to come up with my plastic moment. And then provide some example calculations as well to help you define those. Again, after reviewing the discussion in the determination section of the routine navigating design for routine bridges guide, and then looking at the NHI course material, I can feel confident in developing the section properties. My steel only section properties, my composite section properties for 3N, and then my composite section properties for just the N, the short term. And then likewise, I can go ahead and compute my plastic moment, my yield moment, using all that information. That's only a click away from the design guide. So let's talk a little bit more about constructability and what's provided in the guide for that. Again, my objective here is to perform Girder Flexure design for constructability. So again, I'll go right back to the general flow of design tasks on page 15. Go ahead and click on Girder Flexure design, constructability. Similar page. Each one of these is contained in one page, and you can see I have my green section, my yellow, my orange section, and my blue section. So what's here in the green section with regard to the applicability of the AASHTO LRFD bridge design specifications and the discussion? Well, you can see there's discussion on constructability itself, flexure, shear, deck placement, dead load deflections, and then also tension flanges with holes. These are things I need to consider or would consider as part of the constructability check, and things I would have to walk through. But here, an interesting note here right with constructability is, look, there's a flow chart. What does that mean? Let me go ahead and click on that. It tells me, in the Appendix C of the AASHTO LRFD Bridge Design Spec for Chapter 6, there's a flow chart that goes along with Article 6.10.3. Is this applicable? Yes, it's applicable. And what does the section tell me? Well, it tells me that there is this flow chart with regard to constructability in the AASHTO LRFD Bridge Design Spec. And it tells me the flow chart is applicable to the routine steel eye-girder bridges covered by this guide and is strongly recommended for use in conjunction with this guide. Well, strongly recommended means I should probably go take a look at it. So here's the flow chart that's in the AASHTO LRFD Bridge Design Spec. It walks you through what you need to check. You heard me talk before about dead load deflection. The flexure checks, with regard to local buckling, lateral torsional buckling, and web bend buckling. Holes in the tension flange is there too. And last but not least, the shear checks. So everything that was in that green section of the guide is also shown here within the flow chart for constructability. Again, helping me walk through these design checks, whether or not I'm doing them by hand, by spreadsheet, or I'm reviewing someone else's work with regard to this. This serves as my checklist. This overall guide serves as my checklist to make sure my counterpart doing the design that I'm checking has gone through all the proper design provisions. Then also in the quick links for helpful industry design guidelines and references, right back to that reference manual again. It provides useful information in the direct sections that apply to what I'm looking at for constructability. And you can see we have several examples and several you laying out the deck pour sequence, how to lay out the deck pour sequence, how to get the moments from that deck pour sequence, and how to apply those to my constructability checks. And also I can look at the examples that are part of the Steel Bridge Design Handbook. And, if I open up that Steel Bridge Design Handbook and I go to the table of contents, you can see a lot of the things that are mentioned in the guide that we're talking about here today. Deck placement analysis, flexure for the top flange, flexure for the bottom flange, shear, and then the concrete deck stresses as well. Again, give me all the information I need to be confident in developing these and performing my calculations to develop my girder design. Last but not least here, it says, in addition, sanity check initial design results by comparing them to NSBA span to weight curves. What if I click on that? Well, that takes me right to the NSBA steel span to weight curves. And what this is, it's a really good resource to kind of to actually check, how close you are to a whole bunch of other girder designs. What do I mean by that? Well, this resource is a graphical design aid that can be used during design and for evaluating alternative structures with regard to steel. It allows you to quickly determine the relative bridge weights of various girder spacings for the number of girder spans. The curves here have been constructed from about roughly 800 different conceptual solutions that NSBA has prepared over the last dozen years or so. They represent predicted pounds of steel per square foot of various span lengths and girder spacings for single spans, 2 spans, or 3 or more spans. So I can come in here with my maximum span length and see, based on my girder spacing or based on how many spans I have, what kind of pounds of steel, pounds of girder weight should I have per square foot of deck area to kind of get a ballpark idea if the girder I'm designing is in the right ballpark of most other bridges of that same type. So again, the guide links me to the resources I need to use as a designer. And again, using all those resources available for me, if I go back to our example, I can review the deck. I can develop the deck placement sequence based on the discussion provided in the Steel Bridge Design Handbooks, as well as the NHI course manual. I can do my analysis, come up with my moments and shears based on that. And then I can feel confident in performing the calculations for strength 1 and strength 3, my local buckling resistance checks, and then also my lateral torsional buckling resistance checks as well as my web bend buckling checks, which I don't have shown here. So using all that information, using all the resources available to me, I'm able to do that. So lastly, I kind of want to demonstrate how I would use this guide while doing a field splice design. What do I mean by field splice design? Well, girder pieces can only be shipped at a certain length. So many of my girders are going to be longer than that length, or it'll be 120 feet, 130 feet, or maybe even 150 feet, depending on the location of the bridge and the shipping resources available. So I'm probably going to have to design a field splice to connect the girder field pieces together. So what does the guide tell me? Again, I'll go back to the general flow of design tasks on page 15. I'll click on Splice Design. And we saw Dominic walk through this a little bit, but I'm going to walk through it a little bit more. First up is the green box, the quick links to the applicable AASHTO LRFD bridge design spec provisions with discussion. So let's go ahead and click on flange splices and see what the guide spec or see what the guideline has to say about that. Again, I come here. Yep, it's applicable, right? Again, as long as I have a field splice in my bridge, and I'm going to have to look at this particular section, right? And it explains to me the general parts of a splice: the top flange splice plates, the web splice plates, the bottom flange splice plates, and then any filler plates if I have changes in thickness at that particular splice. Flange splices, it tells me, generally consist of 1 plate on the outside of the flanges and 2 smaller plates on the inside of the flanges, on the web side of the flanges. The web splice generally consists of 2 plates, 1 on each side of the web, that are the same thickness. That's good to know. What else does it tell me? Well, it tells me something about the minimum design forces as well. Bolted flange and web splices are designed for a minimum of 100% of the individual design resistances. Sorry. The flange splice is the smaller design yield resistance of the flange on either side of the splice. And then the web splice is a smaller factored shear resistance of the web on either side of the splice. So it kind of gives me some general parameters on what I'm going to be designing this splice for. So how about some helpful industry design guidelines and references and examples that are out there? Well, you can see there, the reference manual is also shown. There's some collaboration guidelines, as Dominic had mentioned. What about this last one? NSBA's bolted field splices for steel bridge flexural members, overview and design examples. Let me go ahead and click on that. That'll take me right to our resource on this, on bolted field splices for steel bridge flexural members. This particular guideline has 3 examples in it. It goes through some overview of the new design procedures that came along in the AASHTO 8th edition, AASHTO LRP 8th edition. It then walks through 3 different design examples. The examples include a splice of an eye girder and a typical medium span plate girder bridge, a splice for a deeper eye girder bridge, and then a splice for a tub girder bridge as well, which obviously would not fall within this routine design guide. But you can see it walks through, it gives you information on the calculations associated with the design of a field splice, and then provides some example calculations as well, walking through each of the design checks that are needed. That's a pretty good resource, I think, and gives you a lot of information with regard to how to perform these calculations. But maybe I don't want to do the calculations by hand, or maybe it's good to know those calculations by hand. What's this quick links to useful tools? Well, this is the NSBA Splice program or spreadsheet. It's a Microsoft Excel based spreadsheet that is available for free at the NSBA website to help you design field splices. Let me go ahead and click on that. And as Dominic showed before, it takes you right to the website that houses the NSBA Splice spreadsheet. You can go ahead and download this for free. We do ask for some registration information, so when we make updates, you are alerted to those updates. And as I said, it's a spreadsheet. It allows you, the designer, to quickly analyze various bolted splice connections to determine the most efficient bolt quantity and configuration, and design the plates as well. It is updated for the latest and greatest AASHTO LRP 9th edition. And as I said, it's a pure spreadsheet. You input all your numbers with regard to loading, your materials, your plate sections, and so on and so forth. It's a really easy tool to use to design a splice. Now, I'll say, go ahead and use the splice spreadsheet, but be aware of the calculations. Run through an example calculation or two so you become confident and familiar with it. Use the examples that are provided in that NSBA guide that I just showed previously, and understand what calculations are going on behind the scenes. So in my example bridge, I would go ahead and plug in my moments, plug in my shears, do everything with regard to the sections that I'm using, the girder sections that I'm using, and I'd be able to come up with a splice relatively easy that I could use on my particular example bridge. I could back check some of the calculations that were performed by the spreadsheet by using the example calculations and the calculations shown in the reference that was given, and I can use the NHI reference as well. So now let's just move on to the summary here real quick. We talked about four main topics on how I would use this guide. Of course, there's plenty more. Now, I'd use the guide as a designer, then also as a checker to make sure the person that doing the design went through the proper procedures in accordance with the AASHTO LRP bridge design spec. We talked about live load distribution factors. We talked about Girder Flexure design for constructability, and then splice design. And for each of those, we walk through each section of the guide, right? For each one of those, we talked all the quick links, right? We talked about the quick links for the AASHTO LRP bridge design provisions with discussion whether or not a particular article was applicable to my design. We talked about how the guide provides direct links to the resources that are out there, to provide examples, to provide you more information to make you feel more confident in your design and your calculations you're performing. And last but not least, we reference different design tools that are available to you for free to help you, perform calculations that are associated with your design. Again, all of this is meant to provide a roadmap or provide a checklist for you as a designer to all the resources that are available out there to help you walk through a routine design, to help you navigate the AASHTO LRP. As we talked about before, the AASHTO LRP is pretty large. There are a lot of pieces and parts in there to help design many other bridges that are not just routine steel eye girder bridges. It's thick, and there are a lot of article sections in there. Well, we're hoping that this navigating routine steel bridge design guide helps you get over the hurdle of the AASHTO LRP bridge design spec, makes you more confident in your designs, and helps you streamline your designs and makes you more efficient at performing these designs. You can download the new guide right at our website, aisc.org/NSBA. and help and you use it and use it to help you develop efficient COI girder bridge designs on routine bridges.